As a team, we aim to build a pair of robots that could compete in a soccer-like game with each other. One robot searches for and collects a ball, while the other attempts to defend a goal. The main focus of the project was to develop two unique robot models that could simulate a relatively engaging AI competition, a robo-sport. On the physical side, we needed to develop new model designs to facilitate the more complex interactions between the robot and ball. We needed to develop a grasping mechanism, a shooting device, and a blocking component in addition to modifying some of the existing features from the robot provided in Homework 8. To make our robo-dream a reality, we needed to do a bit of research. Since our project is entirely executed in Gazebo, we needed to learn how to use Gazebo to generate interconnected parts that would allow us to perform complex manipulations of the virtual world, such as grasping, kicking, and defending, alongside computer vision, movement planning, and object detection. 3 of those topics were already included in earlier projects from the semester, so, using those lessons as templates and some reading of the documentation, we built off of the examples provided to us. And after many iterations, we had a general idea of what we needed to accomplish. We divided the project into roughly 2 digestible parts, to allow for some parallel development of the project. We had 2 major goals: making 2 robot models, and then developing high-level decision-making for them. And to start the project off, we needed to do a bit of work on the robot model. After spending a while trying to use the Gazebo model editor, our team remembered how the models were generated for previous lessons, and we switched to a generator-driven model using Ruby. Our team modified the Ruby scripts that generated the robot STF models for Homework 8 to instead generate kicker and goalie models, as well as a soccer field world stage. These scripts used defined lengths and angles that made modifying small elements of the design easier, and also allows us to generate a random ball placement for more interesting games. But models alone can't play a game. To generate the various movements necessary to play a game, we needed to modify the existing publisher-subscriber interface. We did this by creating 2 new topics that are then pulled and translated into joint state controller modules running on PID controllers. One topic controls the arm angle, and the other controls the kicker position. We discovered while setting up these controllers that a default PID wouldn't work well with our robot. The piston was loose, and the arms would flop around. To combat this, we added friction to the joints, but then the opposite problem occurred. The controllers wouldn't hit the target positions. After tuning the PID controllers for a while, our solution was to generate high P error values and limit the force applied in the Gazebo model. This allowed the PID controller to accurately hit the positions that we wanted to, while also maintaining a constant force output. After developing these models, we could then focus on the higher level decisions that each robot must make in order to play the game.
The kicker bot, or player bot, is a modification of the robot from Homework 8. We have modified it so that in addition to the camera and sonar, it now has a gripper and a kicker function. The gripper are the 2 arms, and they open and close in order to collect the ball and bring it over to the shot position. The kicker is then used to launch the ball towards the goal. The kicker uses the task-lib library in order to conduct its tasks. So it starts off with a main task, which then launches the collect task, wherein it searches for the ball using CV in order to identify the orange color, and then it turns and drives to that position. Once the kicker robot is close enough to the ball, it closes the grippers around the ball. Once the ball is collected in the gripper, the kicker collect task is complete. Now, the robot needs to move into the shooting position. It does this by using the move command to an XY coordinate based off of the goal and shooting angle. So then it uses the turn to and go tasks in order to reach that spot. Once it has reached that shooting position, it then opens the gripper and kicks the ball. Then it has completed its tasks and is ready to go and search and collect the ball again. This continues until the program is halted.
To protect the goal, we developed a specialized goalie bot. The goalie comes with 2 grippers that are used as arms to defend against the ball. The goalie drives in 2 directions, left and right, across the span of the goal. The strategy used to defend the goal is a combination of strafing and computer vision. When the goalie sees with his camera that the ball is within a predefined distance, it pauses until the ball has been deflected or removed from sight. After the goal is safe, it then continues to strafe across the goal opener. The goalie's current strategy is simple. It doesn't actively search for the ball. Instead, it reacts when a ball appears in his field of vision. Although this works, there are definitely improvements that could be made to our approach. One improvement would be to track the ball and move to an informed position on the goal opener. However, this is difficult because of the speed of the ball and the speed of the opposing robot. The goalie would need to not only examine the distance from the ball, but it would also need to predict the angle at which an opposing robot might shoot the ball. The goalie would need to process a lot of information, determine a course of action, and drive very quickly. Because of this complexity, the above approach wasn't feasible in the time limit.
My major contribution to the project was my task library, which I had used in previous assignments to manage robot behavior. The initial version I had developed after the first maze assignment, and continued to adapt it for later assignments. It uses a stack of tasks where we pull the topmost current task to make progress, and which can schedule new tasks on top of itself or complete to defer back to its parent. The inspiration for it comes from the idea that larger tasks can be decomposed into smaller tasks. Take the example of cooking a meal. There's a few steps that this could be broken down into: preparation, the actual cooking itself, and cleanup. Then, for example, you could break prep into other tasks for cutting and chopping each ingredient. If you think of this like a tree, then using a stack to model active tasks makes the most sense. So with that idea, I added more features to this model for each application I used it for, and added a few ways for tasks to interact with each other. This made tasks very reusable. In the first gazebo assignment, the entire behavior from my robot was implemented in the top-level callback function. It was fairly straightforward, so this was fine. In the task library, the callback function calls into a small runtime that manages the high-level lifecycle of tasks and is essentially a modular state machine. When implementing a new task, you implement a pull function on an object, which is called repeatedly when the task is currently executing. Since we're in an asynchronous environment, you can almost imagine the task stack as a separate asynchronous call stack. Queuing a task is not unlike waiting on a future. Runtime internals aside, one task that was important for us was the go task, which keeps a robot on a particular heading and moves forward, accounting for wheel drift using a PID loop. Wrapping this is a move towards task, which lets you specify an XY position to move towards as a destination. This was useful for breaking up the behavior of the kicker robot between searching for the ball, grabbing it, and kicking the ball towards the goal, among other things.
So first, we needed to be able to take an image and use some simple filtering techniques to mask out a known colored ball from an image. We can make do with the camera's FOV alongside the location of the mask in order to determine the direction of the ball. With this known, we then expanded upon this technique by using the visual angle formula alongside the proportion of the image that the mask takes up, the FOV of the image, and the known size of the ball to determine the distance between the robot and the ball. These two components together would allow us to plan a route for the robot to pick up the ball and send it to the goal. Additionally, the last component would also be used for the goalie to detect where the ball is. The last component we needed would be for the robot to find the ball whenever it's not in frame. We achieved this using some simple scanning in place until the ball showed up in the frame. This imaging library was used within the robot and goalie tasks to locate the ball for pathfinding and also for defending. Some small hurdles we had arose with color keying techniques for the ball. In previous homeworks, we were able to sort of cheese the imaging because we knew the exact color of the sky, shadows, and floors with a very uniform RGB hex value. However, given the spherical nature of the ball and, the nature of lighting in general, we couldn't use quite as rudimentary of a pure RGB filter. So in order to overcome this, we actually found that we could switch our images over to a hue, saturation, and value color space, as this would allow us to greatly reduce the amount of range in the hue component, which is the sort of most important component in determining which color is what, and this allowed for much greater flexibility and less error when introducing things like shadows, which the ball happened to do. Another minor issue we had was finding the center of the mask for determining the direction of the ball. Initially, because the ball shows up as a sphere, we kind of determined that the tallest pixel of the mask would be sort of the center of the ball. However, due to some aliasing of the mask and some unsightly artifacting, it found that there could be multiple top pixels of the ball mask. So we found instead a more robust approach would be to actually sort of find the midpoint given the entire size of the mask, and that would allow us to accurately determine which column is sort of the center of the mask, and once we know the column, then we were able to subsequently find the exact direction.
Thanks for watching. Goodbye.